but it is normalized by temperature over the magnetization. And the reason you do that is so that you can compare it with literally the standard. And the standard in this case is the standard platinum resistant thermometer, which is actually what is used in part to make this traceable to the SI. Specifically to the International Temperature Scale of 1990. I'm happy to talk about that for people who are really interested in standards. So you can kind of see here, this is the thermosensitivity of our PRTs. This is where we're at, well above that. And you can see we're above the PRTs, and in pretty much every case our PRT is down here. To put this in very concrete numbers, the best one that we have is our nickel platinum, which is up to 32 times better than a PRT. And it has a pretty good temperature range. If we go to cobalt platinum, we can expand our temperature range. But in practice, we've been doing a lot of work with our interacting ferrites. And this is just to demonstrate that you can actually do it. So this is temperature measurements at a variety of temperatures, and you can clearly see the change in the signal that you get off of this. Questions? Yes.
What would be the spatial resolution of your method?
So the best spatial resolution that we've gotten is better than 250 microns.
Thank
you. If you go just back one slide, not all of your nanoparticles have the same signal. So how can it be a standard?
So actually the phantom that was used is over here, and we had actually different concentrations in each one. But you can, when you take the ratio, you can calibrate for that. This was one of our early tests where we were just looking to see if we could see the difference. But there's a special cryostat that you have to use in order to get the traceability. Yes?
Why is it like 7th harmonic or 5th harmonic?
So the higher the harmonic that you use, the better your spatial resolution. And so we were always trying to work with the higher harmonics to see what to see how good the thermosensitivity was that we could get. So this next section is on magnetic nanofluid hyperthermia. And the basic idea for this is that you have a magnetic nanoparticle, you apply an AC magnetic field, this time up in the hundreds of kilohertz, and you want to generate heat. And so the first thing to understand is the magnetic nanoparticles you're using for this are never superparamagnetic. If you have a superparamagnet, you don't have heat because you don't have any area in the hysteresis loop. So these materials are always ferri or ferromagnetic. But if you take kind of an ideal hysteresis loop over here, one of the parameters that really matters is the magnetic anisotropy. That's going to influence what your coercive field is. It also tells you what kind of amplitude of your AC magnetic field is that you have to use. Just to demonstrate that I'm not making it up when I say that you've got to have an open loop. So this was a measurement that was done at 10 kilohertz on some nanoparticles. You can see a little bit. As you increase to 25 kilohertz, it opens it up significantly. By 100 kilohertz, it's collapsed back down again. I'll note that the field amplitude is only 2.5 millitesla, so it's a pretty small field. And just to prove that the heat generation does correspond linearly with magnetic anisotropy, we were able to measure the magnetic anisotropy as a function of the applied magnetic field, and you can correlate that with the heat generated under those same applied magnetic field correlations. So there is a linear correspondence. So for magnetic nanofluid hyperthermia, one of the things that you really want for applications is you want the maximum amount of heat output at the lowest possible field. So if you think about trying to treat metastatic cancer with this, you don't want to have to be generating very large magnetic fields over the entire human body over a 6.5-foot area, because if you're going to have to do that, you're going to end up needing your own substation just to power a single piece of equipment. It's a little bit of a problem when hospitals are looking at buying equipment. So we had a series of samples. They were all ferrite-based materials, and we got very different heating from them. We had one that didn't heat very well, one where we got pretty good heating at low fields, but it flatlined. And then we had one where we got even better heating, but it took more fuel to do it. And in the interest of time, I'm going to skip a little bit. And it turned out that there were two factors that controlled this. So the first factor were the interactions. If we had interactions in this material, then that was actually a good thing because it enhanced our magnetic anisotropy, and that enhancement gave us more heat output. But the magnetic domain structure also really mattered. So in this case here, where we got very high heat output, but it took a higher field to get there, we actually had a multi-domain structure. If we had much higher heat output at low fields, we actually had a core shell, where we had the core was a single domain, and then the shell was pointing in a different magnetic direction. And then we had both weak interactions in the multi-domain system. I affectionately refer to this as the plum pudding model of the magnet, because you had lots of different domains that were spread out. I think I will skip this next section in order to get on to cryopreservation. So one of the problems that exists worldwide is organ donation. And if you look at what happens when somebody, say, dies in a car accident and they agree to donate their organs, you have about 4 to 8 hours in order to get that organ to the person that it needs to go into and actually put it in that person. Because otherwise, even putting them on ice, they start to degrade, and once you get a certain amount of damage, there's no point in putting it into another person because it's too damaged to function properly. And as part of this, you're testing for rejection, so how good of a match is it? Can the person get to the hospital in a timely manner to do this? And so the end result is that for most organs, the number that actually make it into a recipient is only order of a few percent. Kidneys are abnormally high, and that's because we have two. And so people can donate a kidney from a live, healthy person into someone who needs one. And so the transfer rate is much higher in this case because you really just have side-by-side surgeries and neighboring organs. But what would happen if you could freeze it, if you could cryopreserve the organ? Now all of a sudden your transit times go from 48 hours to all of a sudden you can have a week or more, and you can move this anywhere around the world. You have time to really test for rejection. You have time to make sure people can get to the hospital. So how would this kind of process work if you could do it? So the idea is that you put these nanowires into some sort of cryopreservation agent inside, say, a heart, and then you freeze it. So you pull it down to liquid nitrogen temperatures. When you're ready to use it, you use hyperthermia in order to warm the system in an AC magnetic field, and then you rinse out your cryopreservation agent. And in the process of doing this rinse, you're removing all of the nanowires. But one of the requirements for this is you need a method when you're cooling for doing a very rapid cool, because you don't want vitrification of the ice. You don't want to form big crystals because they'll break your cell walls and damage the organ. But also when you're warming, you need the same thing. You need something that's very rapid and very uniform. And so depending on what cryopreservation agent you're using, you have a variety of different warming rates. So this is something that's quite reasonable at about 185 degrees Celsius per minute. So how do we do that? Well, we're going to use magnetic nanowires because now all of a sudden we're not trying to put them in the bloodstream. We don't have to worry about the aspect ratio on them. And so you can use the shape anisotropy present in the nanowires of these materials. And in doing that, the really nice thing is you can get very high heating rates on the order of 1,000 degrees Celsius per minute. So you're well able to achieve the warming rate that you need in these materials. And this is really controlled by the magnetic anisotropy and the choice of cryopreservation agent. Questions? Yes?
How long would it take to heat up an organ? I know you said 1,000 degrees per minute, but I can't really relate that to like a heart, for example. How long do you think it would take?
So ideally warm them up pretty rapidly. So you want them to warm up on the order of a few minutes. It's a pretty rapid process. This is a technique that is already very well established for like in vitro fertilization work, so like cryopreserve eggs and embryos. But there, the warming rates are generally more on the order of like 32,000 degrees Celsius per minute. So you're talking, but you have a very small mass. This is a much bigger mass. That's why the uniformity becomes something that's very critical. Yes?
You could comment on how to achieve uniformity.
So the nice thing about these is you actually freeze them with a cryopreservation agent inside, and so you can actually use the blood vessels. And so it gets distributed throughout the vascular system in the heart, and so that means it's well distributed, and because it's not attached to anything yet, you can actually just flush it out at the end. And so that actually gets around a lot of the restrictions on the particular types of materials that you can use for it.
Hi, it's maybe a naive question, but the result is these nanowires are metallic. So do they not damage the cells as they pass through? Like, or are they quite soft so they don't doesn't cause any scarring? Or, I just imagine like metal bits flowing through a heart if that would cause damage.
They're not actually flowing through the cells. They're actually going through the vascular system, and they're smaller than like red blood cells. So if you were to make them really, really long, then you can create a blockage, which if there was a live person would be an embolism and cause a heart attack, but it's not. And so these tend to be on the order of, on the order of 10 nanometers to up to 100 microns, but realistically you're typically less than a micron.
Yeah, so real quick, how do you ensure, I guess talking about almost following up on that, how do you ensure that the wires are, because you said that you wash them out, so what's your method of ensuring that they do all come out, or is it okay that some remain in?
It's just a process of flushing. You're flushing with, for example, water, or in reality probably saline, at fairly high velocity and fairly large volumes. Because saline is very cheap in comparison with doing the actual surgery. And so it's just lots. At some point it becomes a volume issue.
Yeah, okay.
Elena?
Yeah, so for cryopreservation, like you mentioned, IVF and so on, you don't have all the embryos or eggs that survive.
You would not use this technique for embryos because there's nothing around it, and so there's very good methods because that already exist, because you basically freeze them in capillary tubes, and so you get good transmittance of the heat.
But so my question is, do you have any idea on the survival rate of these organs once they are frozen?
This is still a work in progress. So, yeah. So, no. Yes.
I have a curiosity that might be a very stupid question,
Ask.
but there is any possibility, let's say, that this nanowire might change or increase the possibility of rejection of the organ by the recipient, let's say?
The rejection is actually immunological, and so for vast oversimplification of the immune system, because I am not an expert in the subject, the immune system is able to recognize self versus non-self. And like autoimmune diseases are because the immune system gets confused about what self versus non-self is. So the rejection is that if it is not a close match, then it readily triggers the immune system. But anybody actually who gets an organ transplant is on immunosuppressant drugs for the rest of their life. And that actually carries with it its own risks, because those term will cause kidney and liver damage and various other problems. So the closer the match you can get, the lower the dose you need. You can get a perfect match, then in an ideal world you don't need them, but I would not make that statement because I'm not a medical doctor.
But let's say there is no reason of thinking that these nanowires might change the quality of the match, let's say.
No, because they're not going to impact the immunological response.
Thank you.
To be honest, if you have any left, the immune system is going to gobble them up and spit them out very rapidly. Nanowires can't be used in most in vivo applications because our immune system is primed to recognize elongated things because bacteria are elongated. So the circulation time is less than a second.
Hi, so why do you use iron and cobalt alloys? They are known for being quite toxic for cells.
Because they're not going in the cells, they're not staying in the system, but they have really high heating rates, much higher than iron oxide.
As far as I know, there are some research on actual iron cobalt nanoparticles killing like cells being outside of them, because they have quite a high toxicity compared to like oxides and stuff like that.
So there are all sorts of different reasons for toxicity. But one of the things that you need to remember is that these are cold. So they're not immunological, or they're not active in the way that they are at room temperature. And so you can get away with a lot more. The other thing is that you do have separation from most of the cells. You're just around the inside the blood vessels. And so the expected impact is minimal. Primarily where cobalt has an impact is primarily because you need a little bit of it in your diet, but if you have too much, it starts affecting other enzymatic reactions. And those are going to be very slow because it's just low temperature.
Thank you.
May I continue just a little bit? I know I'm running over. So the final section is on nanostructured magnets. And so for those of you who work in spintronics, you may go, oh, I really don't need to worry about that, but actually this has implications for you too, as I hope you'll see as we kind of go through this. So I'm going to differentiate here between hard magnets, also known as permanent magnets, and soft magnets. And the primary way that you differentiate these is with regards to the coercivity. So for a soft magnet, you're generally dealing with a coercivity less than 10 amps per meter. For a hard magnet, you're very clearly dealing with something on the order of about 10 to 100,000 amps per meter. And then you have all sorts of stuff in the middle. So you can see this is coercivity. You've got your rare earth permanent magnets, your hexaferites, alnicos, and your steels. And then you get down here, when you get to your very low coercivities, you get into different kinds of ferrites, your amorphous alloys, and your nanocrystalline systems. But if you look at a hard magnet, one of the things you're looking at is generally, or very specifically, is your hysteresis loop. This can be M versus H, this can be B versus H. The parameters that matter are your saturation, so whether it's BS or MS, you want that to be as large as possible. And your coercivity matters, you want that to be as large as possible as well. Ideally, you also want a high Curie temperature because you want this magnet to be a magnet at elevated temperatures for your applications. The other thing that matters is what's called the energy product, or BH max. And this is basically this maximal area underneath the curve here. So if you're trying to make these kinds of materials, one of the main things that you can control is the magnetic anisotropy. And in doing this, you want to reduce the dimensionality because your symmetry, because the lower the symmetry in general, the higher your magnetic anisotropy is going to be. But there's a trade-off, and this trade-off is pretty prevalent when you start to look at different materials because, for example, the hexaferites are hexagonal, so they have a lower symmetry, but they have a very low saturation magnetization. So it's easy to get very high anisotropy, but you get low MS along with it. You can get a high MS, but then you get a low anisotropy. So you've got a competition here. And so a lot of the work in hard magnets been all about how do you overcome this contradiction. So this is this energy product I mentioned, and you can look at it as a function of the different classes of materials. So the highest energy product is, of course, our neodymium iron boron, specifically neodymium-2 iron-14 boron, and that has a BH max of about 512 kilojoules per meter cubed. I want to point out this one, because a very popular one as well is your samarium cobalts. And if you add a little bit of nitrogen into the system, and very specifically you place the nitrogen around your samarium rare earth, you're able to increase, by changing the crystal field in that area, you're able to increase the anisotropy, but you're also able to increase the curing temperature of the system. And so this was a game that was played quite a bit. So one of the things that they're looking at now is they're looking at nanostructuring these materials. And I mentioned before that they care about the placement of the atoms. So an example of this is actually iron platinum. So most of the iron platinum we work with will end up in the A1 structure. It's a face-centered cubic, but the probability of having an iron or a platinum at any particular location is equal. And so because of that, you have a particular type of symmetry, your magnetic anisotropy is lower. On the other hand, if you form the L1O phase, which is also a face-centered cubic, that means that you have one of them that is located in the space center. And so each position has a different probability. You've lowered the symmetry, you've increased the magnetic anisotropy substantially. And you can see that in these nanoparticles where you've increased the coercivity out onto something on the order, in this case, of about 30 kiloersted. Forgive me for units crossing all over the place. Another way of doing nanostructuring is actually to do multi-layers. So this is often done with nanoparticles, doing core shell or doing some sort of granular matrix. But there's two basic classes. There's what's called exchange spring magnets, where you have a hard layer, a soft layer, and another hard layer. And then exchange bias magnets, where you have an antiferromagnet, a ferromagnet, and an antiferromagnet. And the basic idea is that your hard layer here will pin the soft layer. So you get the MS enhancement from your soft layer, but you get the coercivity enhancement from your hard layer, which makes your loop overall significantly bigger. And so you get a much larger energy product. It's a similar idea for the exchange bias, where you get pinning at these interfaces. So again, you combine the ferromagnet with the coercivity of the antiferromagnet. Where do we use these? We use them, of course, in motors. That is one of the biggest applications. Neodymium iron boron has kind of been a victim of its own success because it works so very well and has such a very high energy product. There are so many new applications that have developed, especially things like wind turbines. And the basic idea there is you have a permanent magnet, which is going past a stator winding, which is just a wind of coil. As it moves past, you have a dB/dt, which is going to induce a voltage, and you get an electrical output. So that would be an electrical motor. You also have speakers. The basic idea, again, is you have a magnet, you have a coil of wire, and when you run the signal in from, say, the piece of music that you're playing, that will change the magnetic field produced, which is going to move the magnet, which will then translate the vibrations into basically a membrane, which will then vibrate and make it an acoustic sound. For soft materials, again, what you worry about, you want a very large saturation magnetization, and you want your coercivity generally to be as small as possible. The other thing you care about is the permeability. So in M versus H, this is susceptibility. In B versus H, this is permeability. Coercivity is, of course, extrinsic, as is the permeability. They're going to depend on the processing and the materials. So what you're looking for in a good soft magnet is as high of a saturation magnetization as you can get, as small as a coercivity as you can get, which also means a very small magnetic anisotropy. You want a small magnetostriction. So magnetostriction shows back up in this case, And that's because if you think about a transformer core, which is one of the applications where you're doing 60 cycles per second, if the thing is physically stretching and contracting and stretching and contracting, that's a lot of stress and strain on it, and you're going to get failure in the very short term, whereas if you can minimize the magnetostructure, the material will last much longer. And then depending on the application, you can want a high purity temperature as well. So processing, it turns out, really matters on these materials. And one of the things that they look at is what's called the Hertzer diagram, which is a plot of the coercivity as a function of grain size. And it turns out this is simply due to the competition between magnetic anisotropy and exchange. And the ratio of these two, the square root, relates back to the exchange length. So for large grain sizes, magnetic anisotropy is going to dominate, and so your dependence is a 1/d dependence. But when you hit something where you're approaching the exchange length, you very rapidly get a decrease which follows d to the 6th. And this is because exchange now dominates. Your magnetic anisotropy is averaging over a local volume in order to determine it, and that gives you this d to the 6th dependence. And so you want to be working down into these nanocrystalline grain sizes, and this is the idea behind a lot of nanocrystalline and amorphous alloys. So this is a common one called fine nut, which is an iron silicon boron niobium copper alloy. When you originally make it, it has a uniform composition. As you anneal it, you start to get clustering, and these clustering eventually grow, and you form grains that are on the order of 15 nanometers or less. And these are grains, primarily, for example, of like an iron silicide, which are actually in an amorphous matrix. And the important thing is that these grains are ferromagnetically coupled to that amorphous matrix. So this is that same alloy, but now what happens if you don't include certain things? Excuse me. So if you leave out the niobium copper, you're just going to end up with these very large dendritic grains. They're on the order of a micron. If you leave out the niobium, then you will have pretty big grains that are on the order of 100 nanometers or so. If you take out the copper, then things are getting smaller, and they're more equiaxial, and on the order of about 50 nanometers. But it's when you include all of them that you get these iron silicide grains in your amorphous matrix, which is niobium rich. So applications, of course, depend on the material and what frequency you want to work at. I mentioned the most important one, which is probably power transformers, which are the transformers that will step up or step down voltage in transmission lines. And just very, very briefly, there's another area called magnetic refrigeration. The basic idea of this is that when you apply a magnetic field, you align all of the spins. This is going to increase the entropy in this, reduce the entropy in the system, so it increases the temperature. You then connect this to a reservoir, and you can pull this heat off. If you then remove the magnetic field, you're going to disorder the spins. This is going to increase the entropy, so you cool it off, and you can now connect this to pull heat out of, for example, a refrigerator or an air conditioning unit. And one of the things that's quite interesting in these materials, and this was work back from about 2004, was they found that by adding a small amount of iron, they were able to change the grain structure that was inside the material such that they had grains in an amorphous matrix, and they significantly reduced the hysteresis losses. Because wherever you have this kind of hysteresis, you're going to get heat, and that's going to reduce the refrigeration capacity of your material. You could do something similar by texturing, so aligning the grain structure in a magnetic field. And so with that, I hope I've been able to give you a bit of a flavor of what nanostructuring can do, and also what a functional magnetic nanostructure is. And I will come back and ask the questions I asked in the beginning. Did anybody notice a common theme and any correlations between the different sections? And I'm happy to take other questions too.
magnetism?
True, all of it has magnetism, but a little more specific than that.
Then perhaps phase transitions, I don't know. Like, so there was also ferroelectrics, you're looking, which is like which is not a magnetic change, but it's a phase transition nonetheless. And all the magnetism is, you're looking at these changes between states to identify what's going on.
Oh yeah, so that's a lot of where the temperature comes into it.
Yeah, that's it. I guess it's
Yeah. There's another parameter. And it's been mentioned a lot in spintronics as well. I'm sorry? Nanoparticles have this. It's a parameter you have to worry about with nanoparticles. Yes?
Something to do with dynamic.
Yes. So what is the property that will affect reversal dynamics? Yes, magnetic anisotropy. Magnetic anisotropy is probably one of the defining parameters for all of these applications. Did you notice any correlations?
What kind of correlation are you asking?
Well, actually, it's not really a fair question. So if you look in the magnetoelectrics, they use a lot of soft materials. If you look at the nanoparticles, the same kind of granular structure that you're trying to make with the fine met was another processing step for the nanoparticles to make them softer, for example. It shows up in magnetocalorics. Again, a lot of the processing, you create a grain structure and then you surround it with an amorphous matrix that you couple to it. On the hard magnets, it's a correlation with spintronics. You couple it. So you couple it with an antiferromagnet and make exchange bias in order to pin things. So the processing you're doing for these quote-unquote simple magnets translates to so many other things, even if we don't think about it in that regard. So there's a lot we can learn from other fields. Other questions?